Hello and welcome. My name is Alan, and we are back with more ideas and opinions of Albert Einstein. Today we'll be reading two short pieces. The first is called On the Theory of Relativity, and it is a lecture at King's College in London, 1921. And this was published in Mein Weltbild, Amsterdam, Querido Vlog, 1934. It is a particular pleasure to me to have the privilege of speaking in the capital of the country from which the most important fundamental notions of theoretical physics have issued. I am thinking of the theory of mass motion and gravitation, which Newton gave us, and the concept of electromagnetic field, by means of which Faraday and Maxwell put physics on a new basis. The theory of relativity may indeed be said to have put a sort of finishing touch to the mighty intellectual edifice of Maxwell and Lorentz, inasmuch as it seeks to extend field physics to all phenomena, gravitation included. Turning to the theory of relativity itself, I am anxious to draw attention to the fact that as this theory is not speculative in origin, it owes its invention entirely to the desire to make physical theory fit observed fact as well as possible. We have here no revolutionary act, but the natural continuation of a line that can be traced through centuries. The abandonment of certain notions connected with space, time, and motion, hitherto treated the fundamentals as fundamentals, must not be regarded as arbitrary, but only as conditioned by observed facts. The law of the constant velocity of light in empty space, which has been confirmed by the development of electrodynamics and optics, and the equal legitimacy of all inertial systems, special principle of relativity, which was proved in a particularly incisive manner by Michelson's famous experiment between them, made it necessary to begin with that the concept of time should be made relative, each inertial system being given its own special time. At, as this notion was developed, it became clear that the connection between immediate experience on one side and the coordinates and time on the other had hitherto not been thought out with sufficient precision. It is, in general, one of the essential features of the theory of relativity that it is at pains to work out the relations between general concepts and empirical facts more precisely. The fundamental principle here is that the justification for a physical concept lies exclusively in its clear and unambiguous relation to facts that can be experienced. According to the special theory of relativity, spatial coordinates and time still have an absolute character insofar as they are directly measurable by stationary clocks and bodies, but they are relative insofar as they depend on the state of motion of the selected inertial system. According to the special theory of relativity, the four-dimensional continuum formed by the union of space and time Minkowski, retains the absolute character which, according to the earlier theory, belonged to both space and time separately. The influence of motion relative to the coordinate system on the form of bodies and on the motion of clocks, also the equivalence of energy and inert mass, follow from the interpretation of coordinates and time as products of measurements. The general theory of relativity owes its existence in the first place to the empirical fact of the numerical equality of the inertial and gravitational mass of bodies, for which fundamental fact classical mechanics provided no interpretation. Such an interpretation is arrived at by an extension of the principle of relativity to coordinate systems accelerated relatively to one another. The introduction of coordinate systems accelerated relatively to inertial systems involves the appearance of gravitational fields relative to the latter. As a result of this, the general theory of relativity, which is based on the equality of inertia and weight, provides a theory of the gravitational field. The introduction of coordinate systems accelerated relatively to each other as equally legitimate systems, such as they appear conditioned by the identity of inertia and weight, leads, in conjunction with the results of the special theory of relativity, to the conclusion that the laws governing the arrangements of solid bodies in space when gravitational fields are present do not correspond to the laws of Euclidean geometry. An analogous result follows for the motion of clocks. This brings us to the necessity for yet another generalization of the theory of space and time, because the direct interpretation of spatial and temporal coordinates by means of measurements obtainable with measuring rods and clocks now breaks down. The generalization of metric, which had already been accomplished in the sphere of pure mathematics through the researches of Gauss and Riemann, is essentially based on the fact that the metric of the special theory of relativity can still claim validity for small regions in the general case as well. The process of development here sketched strips the space-time coordinates of all independent reality. The metrically real is now only given through the combination of space-time coordinates with the mathematical quantities which describe the gravitational field. There is yet another factor underlying the evolution of the general theory of relativity. As Ernst Mach insistently pointed out, the Newtonian theory of is unsatisfactory in the following respect. If one considers motion from the purely descriptive, not from the causal point of view, it only exists as relative motion of things with respect to one another. But the acceleration which figures in Newton's equations of motion is unintelligible if one starts with the concept of relative motion. It compelled Newton to invent a physical space in relation to the acceleration to which acceleration was supposed to exist. This introduction ad hoc of the concept of absolute space, while logically unexceptionable nevertheless seems unexceptionable nevertheless seems unsatisfactory. Hence Mach's attempt to alter the mechanical equations in such a way that the inertia of bodies is traced back to the relative motion on their part, not as against absolute space, but as against the totality of other ponderable bodies. In the state of knowledge then existing, his attempt was bound to fail. The posing of the problem seems, however, entirely reasonable. This line of argument imposes itself with considerably enhanced force in relation to the general theory of relativity, since, according to that theory, the physical properties of space are affected by ponderable matter. In my opinion, the general theory of relativity can solve this problem satisfactorily only if it regards the world as spatially closed. The mathematical results of this theory force one to this view. If one believes that the mean density of ponderable matter in the world possesses some finite value, however small. So, yeah, Einstein, given his thoughts on the theory of relativity and how it fits into physics. So, yeah. The other piece we're going to read here is called The Cause of the Formation of Meanders in the Courses of Rivers and the So-Called Bear's Law. And this was read before the Prussian Academy, January the 7th, 1926, published in the German periodical Die Naturwissenschaften. I know I butchered that. Volume 14, 1926. It is common knowledge that streams tend to curve in serpentine shapes instead of following the line of the maximum declivity of the ground. It is also well known to geographers that the rivers of the northern hemisphere tend to erode chiefly on the right side. The rivers of the southern hemisphere behave in the opposite manner. Bear's Law. Many attempts have been made to explain this phenomenon, and I am not sure whether anything I say in the following pages will be new to the expert. Some of my considerations are certainly known. Nevertheless, having found nobody who was thoroughly familiar with the causal relations involved, I think it is appropriate to give a short qualitative exposition of them. First of all, it is clear that the erosion must be stronger the greater the velocity of the current where it touches the bank in question, or rather, the more steeply it falls to zero at any particular point of the confining wall. This is equally true under all circumstances, whether the erosion depends on mechanical or on physico-chemical factors, decomposition of the ground. We must then concentrate our attention on the circumstances which affect the steepness of the velocity gradient at the wall. In both cases, the asymmetry as regards the fall in velocity in question is indirectly due to the formation of a circular motion to which we will next direct our attention. I begin with a little experiment which anybody can easily repeat. Imagine a flat bottomed cup full of tea. At the bottom, there are some tea leaves, which stay there because they are rather heavier than the liquid they have displaced. If the liquid is made to rotate by a spoon, the leaves will soon collect in the center of the bottom of the cup. The explanation of this phenomenon is as follows. The rotation of the liquid causes a centrifugal force to act on it. This in itself would give rise to no change in the flow of liquid if the latter rotated like a solid body. But in the neighborhood of the walls of the cup, the liquid is restrained by friction, so that the angular velocity with which it rotates is less there than in the other places near the center. In particular, the angular velocity of rotation, and therefore the centrifugal force, will be smaller near the bottom than higher up. The result of this will be a circular movement of the liquid of the type illustrated in Figure 1, which goes on increasing until, under the influence of ground friction, it becomes stationary. The tea leaves are swept into the center by circular motion and act as proof of its existence. The same sort of thing happens with a curving stream. At every cross section of the course where it is bent, a centrifugal force operates in the direction of the outside of the curve. This force is less near the bottom, where the speed of the current is reduced by friction, than higher above the bottom. This causes a circular movement of the kind illustrated in the diagram, which they have printed here. Even where there is no bend to the river, a circular movement of the kind shown in Figure 2 will still take place, if only on a small scale, as a result of the Earth's rotation. The latter produces a Coriolis effect force acting transversely to the direction of the current, whose right-hand horizontal component amounts to 2VQ sine per unit of mass of the liquid, where V is the velocity of the current, Q is the speed of the Earth's rotation, and I'm not sure what that sign is, the geographical latitude. As ground friction causes a diminution of this force toward the bottom, this force also gives rise to the circular movement of the type indicated in Figure 2. After this preliminary discussion, we come back to the question of the distribution of velocities over the cross-section of the stream, which is the controlling factor in erosion. For this purpose, we must first realize how the turbulent distribution of velocities develops and is maintained. If the water which was previously at rest were suddenly set in motion by the action of a uniformly distributed accelerating force, the distribution of velocities over the cross section would at first be uniform. A distribution of velocities gradually increasing from the confining walls toward the center of the cross section would only establish itself after a time under the influence of friction at the walls. A disturbance of the roughly speaking stationary distribution of velocities over the cross section would only gradually set in again under the influence of liquid friction. Hydrodynamics pictures the process by which this stationary distribution of velocities is established in the following way. In a plane potential flow, all the vortex filaments are concentrated at the walls. They detach themselves and slowly move toward the center of the cross section of the stream, disturbing themselves over a layer of increasing thickness. The velocity gradients at the wall thereby gradually diminishes. Under the actions of the internal friction of the liquid, the vortex filaments in the interior of the cross section are gradually absorbed, their place being taken by new ones which form at the wall. A quasi-stationary distribution of velocities is thus produced. The important thing for us is that the attainment of the stationary distribution of velocities is a slow process. That is why relatively insignificant, constantly operative causes are able to exert a considerable influence on the distribution of velocities over the cross section. Let us now consider what sort of influence the circular motion due to a bend in the river or the Coriolis force, as illustrated in Figure 2, is bound to exert on the distribution of velocities over the cross section of the river. The particles of liquid in most rapid motion will be the furthest away from the walls, that is to say, in the upper part of the center of the bottom. These most rapid parts of the water will be driven by the circulation toward the right-hand wall, while the left-hand wall gets the water which comes from the region near the bottom and has a especially low velocity. Hence, in the case depicted in Figure 2, the erosion is necessarily stronger on the right side than on the left. It should be noted that this explanation is essentially based on the fact that the slow circulating movement of the water exerts a considerable influence on the distribution of velocities, because the adjustments of velocities by internal friction, which counteracts this consequence of the circulating movement, is also a slow process. We have now revealed the causes of the formation of meanders. Certain details can, however, be deducted without difficulty from these facts. Erosion will be comparatively expensive not merely on the right-hand wall, but also on the right half of the bottom, so that there will be a tendency to assume a profile as illustrated in figure 3. Moreover, the water at the surface will come from the left-hand wall and will therefore, on the left-hand side especially, be moving less rapidly than the water rather lower down. This has, in fact, been observed. It should further be noted that the circular motion possesses inertia. The circulation will therefore only achieve its maximum beyond the place of the greatest curvature, and the same naturally applies to the asymmetry of the erosion. Hence, in the course of the erosion, an advance of the waveline of the meander formation is bound to take place in the direction of the current. Finally, the larger the cross-section of the river, the more slowly will the circular movement be absorbed by friction. The waveline of the meander formation will therefore increase with the cross-section of the river. So yeah, Einstein just talking about how a river, a flowing body of water, never follows a straight path, and trying to explain coming how this, why it always meanders, why rivers have these bends and always have these bends and crooks in them. So yeah. um I'll see if I can find copies of the figures in the book, and post them in the description below the video. But as always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.